Hello everyone, this is lecture 4 of PTRE 465531, Petroleum, Reservoir, Geomechanics. Last time we discussed briefly about items from geology, structural geology in particular, that concern us as petroleum engineers. We talked about anticlines, we talked about structural traps, like anticlines, like salt domes, etc., etc. And we did, one second. So we saw a lot of theoretical stuff, words. And then we learned about 3 new terms. We talked about S1, S2, and S3. And those are basically, let me bring it, basically used to describe what we call the 3 in situ principal stresses. We said in the convention that we will be using in this class, which is the same convention that Mark Zobak uses in our class textbook, S1 is the most compressive, S2 is the intermediate, and S3 is the least compressive. And we said in geomechanics in general, we will do the opposite of what we did in solid mechanics. We are going to be calling tension negative and compression positive, so that we don't get to deal with too many negative signs. Now, we talk about S1, S2, S3, and we said there is one rule other than their relative magnitudes, which I think you understood by now. The fact that they are mutually orthogonal, that means each one is at 19-degree angles to each other. That does not exclude their orientation. That does not constrain their orientation. That means of the whole thing. That means as long as they are at 19-degree angles from each other, I need to get the pen. There you go. Okay, it doesn't matter. That means if we are like this, like S1, S2, and S3, we can have that. Or we can be also like this, S1, S2, and S3, as long as they are at 90-degree angles with each other. It's okay. I can, as long as it's at 90 degrees, it's like the rule of the left-hand rule or the right-hand rule. It's okay, as long I can move it as I want, as long as they are at 90-degree angles from each other. And then I need to make sure what I call S1 is what has to be called S1, what I call S2 has to be called S2 and S3. Now, when we do problems, like try to solve problems mathematically, we generally set our frame of reference. So when we have, let's just say the x-axis, the y-axis, and the z-axis, if I'm using a Cartesian coordinate system, I set it up generally in a way that will help me the most, that makes things easier with me. I can do it arbitrarily. So for instance, I can have the S1, S2, S3 configuration that you see in this diagram. Okay, S1 looks up, S2 looks towards me, S3 looks the other way. Okay, and I'm asking a student to solve a problem in regards to this topic, and he has to set his axis. He can set his axis, say like this, X, Y, and then Z. Is it gonna be an easy problem to solve, do you think? What value? Give them magnitudes? No, I'm just saying in general, like he has to solve a problem and he's setting up his axis. If he sets it up like this, he sets his axis like this, okay, but the stresses are like this. So he's gonna have a tough time mathematically to come up with the solution, regardless of what the problem is. He made it hard, or she made it hard on herself because of the setting up of the frame of reference. It's smarter to set the frame of reference parallel to one of the stresses so that it basically will help. Now, if I do it, I might have some angles to deal with, but I might not. If I set it, for instance, Z parallel to S1, then I know at most I might have an angle between X and S3 on the YX plane. I might have an angle from Y to S2 on the XY plane, but it helps things easy. I can be even more easy on myself if possible. Sometimes it's not possible. And maybe set the Z-axis parallel to S1, the X-axis parallel to S2, the Y-axis parallel to S3, or the other way around, the way you see it in this picture. And then I'm basically making it extremely easy on myself. So you see that the way I set my frame of reference, which depends arbitrarily on me, is an arbitrarily, many times is arbitrarily set, completely arbitrarily set sometimes. It can help me or make my life harder. And now, once we proceed from there and try to make some rotation with the matrix to get it to align with the frame of reference, I promise you it's gonna, even if it becomes harder, it's gonna eventually become easier. It's one of those topics that to become easier, it's gonna become harder first, you know? There would be simplifications done. But rotations of matrices, rotations of frame of reference, which involves matrices, it's a little bit of a tough, I was told that this is the toughest concept in this class. Rotation of coordinates, basically. And we're gonna get in slowly, of course. We're gonna dip our feet first, and then we did see this slide about paleostress, and we talked about it. Now, in situ measurements of the subsurface stresses, we talked about S1, S2, S3. We now need to know the magnitude. Say I'm on the field, or I'm in the office. I'm trying to plan and design of a fracture job in a well that is 10,000 feet underground in Grand Forks, North Dakota. I don't know. How do I know the S1, the S2, the S3 from the values and their direction as well? But I need to know them. It's integral part of my design, right? So it is important for me to be able to estimate them somehow and also know their directions. So the easiest in situ principal stress to quantify is the least, as petroleum engineers, is the least compressive, which is S3, right? So we do what we call hydraulic fracture test. That's what my old geomechanics professor used to call them. A better word for it would be fluid-driven tensile fracture test, but you will understand later in the class why this is the case. And we do those tests in a well. Like I have a well, I drill it. It's basically I made a hole underground. It's filled with fluid. I replace rock with fluid, and I am gonna do a kind of test. And I have 3 options, maybe more than that, to help me quantify S3, the least compressive of all the stresses. The first option is an extended leak of testing. Extended leak of test. it's in the leak of test family of leak of test family. It's a lot of there is a lot of names that are basically they do the same thing. Some of them are able to give you additional information, which is more for the next class, I would say. But basically, yeah, during drilling, as I drill, from your drilling class, we drill, then we stop drilling, we run casing, we cement the casing, and we proceed to drill more, further, deeper. Generally, they do this kind of test in between. After you run the casing, you stop, and then you basically increase the pressure of the fluid in the well. You mean by pumping more and more fluid, and you monitor how the pressure increases. And then you see the pressure trend doing some weird stuff. And from those weird stuff, you try to decipher what it tells you for S3. And another way is a mini frac test performed before the hydraulic fracture treatment. And it's similar to the X-Lot, the extended leak-off. It's basically done before you do a fracture treatment. Now the well is already drilled. And you are gonna run a frac job. And before that, you run a mini frac test. Now, just something I missed saying is the fact that when you are drilling and you are doing extended leak-off test, when you are pressurizing, you are gonna pressurize up to the point just before a fracture starts happening, right below the casing, right below the casing sheet. Like the last piece of casing is like the fracture will occur at the shallowest exposed point, and the shallowest exposed point is directly below the casing sheet. So that's why we ran it right after casing and cementing to determine the next weakest spot in the system. Step rate test performed before steady state fluid injection with formation partitioning pressure used as an overestimating proxy for S3. This is a little bit of a more complex step rate test. In fact, in Texas, is mandated by state law. If you are gonna drill an injection well, you need to run a step rate test before that, and you need to make your results available to the regulating agency, government state regulating agency in Texas, which ironically, its name has nothing to do with oil and gas. It's called the Texas Railroad Commission, and there are historic reasons as to why it's called the Texas Railroad Commission. It has nothing to do with railroads. The railroads belong to the Department of Transportation, but the Railroad Commission, it used to deal with railroads back in the day when they were overproducing in the 1930s in Texas. And they wanted to apply production quotas. They had to force people to shut the wells down some days of the week. And it was very hard to enforce them and enforce these rules to basically choke the well down for a few days. So what they were doing is that they had to get an entity that had enough manpower to basically control those people. And it ended up being the Texas Railroad Commission, and that's how the name was stuck. But when you hear the Texas Railroad Commission, it basically has to do with oil and gas. And I know that there is, how do you say, there is an overwhelming, stance from some people that the oil and gas regulation in Texas must be under the Department of Natural Resources, but I mean, that would be weird. Texas Railroad Commissioner used to be one of the most influential positions in the oil and gas in the world. back in the 80s. I know the Texas Railroad Commission office wasn't far away from where I used to go to school from. And when I went to school, there were people in the petroleum engineering department in Texas who knew all commissioners who would say like, I will go to my office on Monday morning, make coffee, and decide what the price of oil will look like in the whole world for that week, you know, because they would be deciding on their production allocations, you know, at the time when there was a lot of oil. Just right now, you have a lot of oil around. If you force people to not produce somehow, you are able to control the supply side.
It's like OPEC?
Pretty much, pretty much. But OPEC is a much larger scale, you know? And it's also conflicting because it's many countries.
Oh, yeah.
Yeah. But also in Texas, it's like conflicting because, I mean, one state, because you have the price goes up when you are not producing, and you think if I produce a few barrels more, I can sell them at this high price. But eventually, it would keep the price going down if you keep doing it, right? So people are producing secretly where and stuff like that. Anyway, but yeah, those three tests, you can run them and process them in a certain way, which we are gonna learn. Read from them what is S3, the value, the magnitude of S3. Yeah, S1, S2, S3 represent in situ principal stresses. The subsurface in situ stress state can be much more complex than what I showed in the 3 slides ago. Normal stresses may not be aligned with the principal directions. So it can be a situation like what I described. You decided to go with a Cartesian coordinate system, which I think makes sense, X, Y, Z, and you set it up in a way that S1, S2, S3 doesn't align. That makes things difficult for you. And now those S1, S2, S3 principal stresses, they are normal stresses. If you remember from your solids mechanics class, we talked about normal stresses and shear stresses. Normal stress is a stress acting perpendicular to a surface. So basically, there is no shear created, no shear effects created from that normal stress. But you may also have shear stresses, which is basically a stress that is creating a motion perpendicular to the direction it applies. And it can be mathematically, it's complicating things a lot. Complex 3D stress states can be expressed with a 3x3 tensor, which is basically a 3x3 matrix. Similarly, 2D stress states can be expressed with a 2x2 tensor. So we had 3 stresses. We talked about 3 stresses, S1, S2, S3. But now we are talking about a 3x3 tensor. So it's something like this. Okay. Like, say you have XYZ system, okay? XYZ Cartesian coordinate.
Kind of
Huh?
becomes kind of
it becomes a matrix. Okay. So I set my system in a certain way. Okay, I have SXX, SYY, SZZ, and I think this becomes SXY, XZ, SYZ, ZY, SYX, ZX, okay. So now my system it has 9 new components, and I know 3 of them, S1, S2, S3. I can have from those S1, S2, S3, the way I set my system, I can get up to 9 different values, or I can be smart and set my system a certain way that I can make, to make my life easier, make as many of these terms as possible to go to 0. It would be ideal if I get all, how do you say, if I can get somehow, if I can get these, yeah, and then the 3 above, make them 0, so I only have this, and this to worry about.
Principal components.
Yeah. Those would be known as the principal stresses, and they will be basically, they would be, we only have 3 non-zero values to worry about. Now, something I didn't say, when you saw this matrix I drew, when the subscript of the stress is the same, so SXX, SYY, SZZ, that means they are normal stresses, okay? If the subscript is not the same, Y and X, Y and Z, X and Z, Z and X, all those, it means that it's a shear stress. Many people use S for normal stresses, and they like to use tau, the Greek letter tau, for the shear stresses.
Structural geology is like that.
Yeah. The Greek letter tau, like this. Okay. Versus S. Sorry. S. Or some people use the Greek letter sigma, but we're gonna see later. Sigma means something different for us. But yeah, and there is ambiguity. You may read some papers, they use a different sort of nomenclature than others. And it's confusing even for me right now after so many years. But yeah, it can be very, very confusing. The idea is that I'm trying to give you the interrelationship between frame of reference and stress state. So when you hear the word stress field or stress state, think that of a matrix, okay? A matrix with, at a given point, if there is, okay, that's the REV, the stress state of this REV, it's gonna be described by a matrix, 9 by 9, which we may be lucky and have some 0 terms to make our life easier. Ideally, as many as 6 0 terms. Hi, Hakim. Mathematical processing is necessary to calculate the in situ principal stresses. And we are going to do some things that you learn in linear algebra, like eigenvalues and eigenvectors. So the direction in which, let's just say, I gave you a stress state and, okay. We did a frame of reference and we were lucky enough, we got it down to SXX, SYY, SZZ, 0, 0, 0, 0, 0, 0. That means we align X, Y, and Z to be in the principal direction, or to make it again easier, maybe it would be smarter if I do it like this, because I want you to use symbols that you already know. Say S1, S2, S3, and everything else is 0. Okay. It means that the direction of those are the principal stresses. They are known as the principal stresses, and their directions, which are going to be given to us by vectors mathematically, they are going to be known as the principal directions, right?
In the previous matrix, so
Yeah.
you have a push stresses in all the directions. So if the stress is in diagonal, it should be perpendicular. What's the name of it?
Normal,
And if it's
shear.
okay, so the others are shear stress.
Yeah, I mentioned it.
Yeah.
So somehow I went from, it was like this.
Mhm.
You need to help me, Malek.
XY, XZ, and your SYZ,
YZ,
and
SZY,
YX,
YX,
and
SZX. Okay. So somehow I went from there, and so I'm going from the right to the left, is based on the space that we have. I manipulate my stress field in such a way that I get S1, S2, S3, and everything else is zero.
So basically, you're assuming that there is no tangential stresses.
Yeah.
It's not assumption, it's the same equivalent nature.
You manipulate them in a certain way. You set the frame of reference a certain way to go from here to here. Now, the process, every matrix can go from this format version to this by changing the frame of reference. My old professor, he had a cube, and he basically colors one side of the cube blue, another side of cube red, another side green, and you move it in the frame in the underlight. You move it, rotate it,
To make it down.
and you see, you see you see 9 different colors because they mix, and then but you can look at it from one particular angle that you see only 3. And that's like the best, I think the video is on YouTube. If you look at Spinoza's
Basically,
Geomechanics.
you're trying to take the best materials that shows the 3 perpendicular.
The best angle, the best angle.
for
It
sure.
depends from where you are looking at it. What I was going to say? It has to do with that, but it is possible. It's just you need to rotate your frame of reference a certain way. And we basically call this version of the matrix the identity of the matrix. It's like the ID card of the matrix. Every matrix has that.
Yeah.
Okay. And to do that, these values are known as the eigenvalues. That's how you find the principal stresses, and you get their directions by the eigenvectors. Yeah. So we are going to have an example of it, but before that, I have a slide that shows better. Okay. Now it's the same problem, but I use 1, 2, 3 coordinate system.
Okay.
This has nothing really to do with S1, S2, S3. It's just, instead of X, Y, and Z, I have this coordinate system. Okay. Arbitrarily set coordinate system. It might as well be X, Y, and Z. Okay, and I have the normal stresses are with blue, light blue, and the others are, the shear are with orange. Something like that, yeah. Okay, so I have the terms there, the components there of the stress field. So I ask you for your stress field at this point, you give me this matrix. You give me 9 values. Okay, now what about I change the frame of reference? Wait, let me go here. Okay, let's forget about those for now. I change the frame of reference a little bit. I twist it, and I get this. And I put P here to show that this is the principal. So it's not the same as just principal. This is S1, S2, S3 from the 4 slides ago, right? Okay, stress tensor. We said that if the subscripts are not the same, it means that they are shear. stresses. So basically is the impact of stress one on is the impact of stress three on the plane perpendicular to the axis of one, something like that. And it goes on for like everything, whatever you learn in multivariate calculus, I believe. And yeah, some people use S, some people use tau. Frame of reference is important. It rotates. You rotate it such that the shear stresses go to zero, leaving normal stresses only in the diagonal. And those are the in situ principal stresses. This is a special frame of reference, and it represents the principal axis. So I take this and I rotate this to get to a point that is like this. If any of these zeros is no longer zero, that means the other three are not the principal axis, the stresses acting in the principal direction. And I think you understand here that okay, S1P is not the same as S11, and it's not the same. They rotate. Yeah, I know it's a difficult concept when you see it the first time. It will become easier. And like I promise, it's going to become harder before it becomes easier, but it will become easier. Calculation of the principal stresses and axes. Okay. You use the eigenvalue, the matrix identity card, ID, to get the in situ principal stresses. To do that, you have to solve what we call the characteristic equation of the matrix. Is the determinant of S minus lambda I. S is the matrix, the stress field matrix. Lambda is the eigenvalues, eigenvectors, eigenvalues vector. And the I is the identity matrix. Okay. That's one thing.
Which means that
the
matrix lambda and S are equivalent.
Yeah. No, the matrix lambda, no.
S and
I. S and I, yeah. Yeah, we're gonna see. S and I are matrices. Lambda is a vector, 3 by 1. And the eigenvector is gonna give us the principal axis directions. It's gonna be given by basically solving this equation for V. And I'm gonna show an example, don't worry about if it looks weird. This is the symbolic form, basically. Zero vector, this one?
Yeah, because it's multiplied by a vector, so it should be vector.
Yeah, but we don't put zero, it's like 0, 0, 0.
Yeah, but zero vector.
It's a vector of zeros, right?
Yeah, so it's not scalar. The scalar is 0.
Yeah, every one of those equations are gonna lead to 0. I never saw a vector on top of a.
Do it because it's not scalar. It's a 0 in a.
I never saw it like so. You want the arrow on top of the.
Well, it's not one value. It's a.
Yeah, it's multiple. Yeah. Yeah, and you plug. So lambda, you get like different eigenvalues, right? You can have 3 different eigenvalues. Okay. For every eigenvalue, you get 3 components of a vector. So a vector has X, Y, and Z, let's say, component, right? Yeah.
Can you repeat, please?
Yeah. So you solve this and say you find 3 solutions, right?
Okay.
Lambda 1, lambda 2, lambda 3.
Yes.
Okay. Lambda 1 has VI1, VJ2,
Okay.
VK3.
Vector of the.
Yeah. And then lambda 2 has the same. VI2, so you get like 3 become 9. Right?
Yes.
So it becomes much more complicated. I mean, eigenvalues are easier to find than eigenvectors. There is one vector with 3 components for every eigenvalue, which basically is one number. 2 Vj,
Two, VJ2, VK2.
yeah. Yeah, this was wrong at the, what I wrote at the top. 1 second. Yeah,
VG1 and VG.
yeah, it was, yeah, I made a mistake, sorry. VK1, let's say, and you don't have to call them this way, but unless I tell you basically, but Vj comma 2, Vk comma 2, and then you have lambda 3 giving Vi 3, Vj 3, Vk comma 3. Yeah, so you have 9, 3 and 9. So lambda 1, lambda 2, lambda 3, whatever, 3 times. It's gonna take, it can be a long process mathematically, but there is something that it's gonna make our life easier. The fact that in geomechanics, let me see if there is, okay. We will see it now. In geomechanics, for stability, the stable stress states are matrices that are diagonally symmetric. That means that if I take a matrix and I put a mirror, yeah, in the diagonal, let's just say I have this mirror. Whatever I see here, I need to see here, right? I see, what do I see? 0, and I see 0. I see 0, I see 0. I see -1, I see -1. So it, oops, sorry. So it makes my life easier when I'm dealing with stable stress fields. That's what I was telling somebody, I don't remember who that. Yes, it's linear algebra, but it's not that terrible, you know? It's a little bit, it's more intense than the math you see, say, in drilling, but what you saw in the previous 2 classes, but it's not gonna be that horrible. I mean, you're not gonna be seeing imaginary numbers and stuff. Nevertheless, you can still calculate the eigenvalues and the eigenvectors of an unstable stress state. It means that, yes, there are temporary eigenvalues and eigenvectors, but it doesn't mean that the stress field is stable, right? So it means we might have some sort of rotation, some sort of motion going on that will eventually, it's gonna be temporary, it's gonna stop. But yeah, when they give you a stress field, it's a good idea to stop and ask yourself, is this stable or not stable? So you see that if it's diagonally symmetric, yes. If not, no. But you can still proceed if it's a no. Sometimes, depending on what the question is asking. So here we have our first example problem. Solve the in situ, made a mistake here. Solve for the in situ principal stresses and directions of a stress field defined by tensor S. And we talked already, and we identified and agreed upon that it's stable. So I asked if it's stable, and we said yes. Okay. So how do we do the, how am I gonna proceed? We want the principal stresses and their direction. We said that the principal stresses are given by the eigenvalues. So I have to solve this equation that we mentioned earlier. Yeah.
On the I.
Yeah, the characteristic equation, set it equal to 0. Yeah, actually the characteristic equation is the left side.
Yes.
Yeah. I do that. And basically I have this in an expanded form. Okay. This is the matrix, and this is the identity matrix. It has everything 0 except ones of the diagonal. And the L is basically a constant value that is going to get 3 solutions eventually, and we have zeros, as Hakim said, 12 vertical axis. Okay, if you remember from, well, let's go to the next step, and now we'll talk about the determinant, because what you have in the parenthesis here can be solved very easily. You multiplied every component here by lambda, so you get rid of all the zeros, and you have only lambda in the middle. So you have minus lambda in the diagonal. You just need to come here and basically say all the diagonal terms have minus lambda. Makes your life simpler. There it is. And now I need to do the determinant. To do the determinant for a 3 by 3,
We do plus, minus, plus, right?
yeah, every other class you do minus after, yeah. So you take this, and then you multiply by these two, yeah, minus these two multiply together. So you do 1 minus lambda, 3 minus lambda square,
Minus 1 square.
well, minus 1 times minus 1.
Minus 1 square.
Yeah, so it's minus 1 basically, right? Okay, oops. Oh, sorry. What did I do? Okay, equal to, I stopped the pen.
Yeah.
Yeah. Okay, so you saw the solution, but it's basically, yeah. I wasn't trying to check on the, so equal to 0, okay. So automatically now I have one solution, lambda equals 1, right? And then I can solve what is inside. Lambda 3 minus lambda square equals to 1, and then I do square root plus or minus 1, and then I do plus. I think the answer would be lambda equals 1, lambda equals something else. So expanded version is, yeah, and then you have basically lambda equals 1, lambda equals 2, lambda equals 4. And I arrange them in the biggest to smallest because like lambda 1 I associated with S1, you know, the more compressive.
Yeah.
2 and then yes.
It's kind of good because the determinant of the whole matrix should be one value.
No, the determinant,
Yes, should be one value.
yeah, it's one value, but you have different values for lambda because they're quadratic.
So it should be the first, it should be equal to 0, not the 0 vector, because it's a scalar, it's a value, it's not a vector. The determinant of
Also, you are saying that this should be 0.
it should be
Yeah,
0.
yeah.
And it should be the first line that you did, minus the second line, and minus the third line.
Yeah. But the rest is they have zeros, so they
yes.
go away.
Yes, that's true.
But I think what you said is right. This should be 0, just 0.
Yeah,
Not a vector.
yes.
Yeah, we'll fix that. That's why we didn't have a vector above the arrow above the other zeros.
But it should still be because it's multiplied by a vector, so it should be.
But it's one if it's one value or
It's a vector, so it should be 3 dimensions, 3 dimensions.
yeah, I guess so. Yeah, I never
Yeah,
saw.
but this is because of zeros we had one line.
Yeah. The rest is if say these ones on the top were non-zero, I would have had minus other terms. It would have become very, very complicated. Yeah. Now, I have my eigenvalues. How about I find my eigenvectors? And we only have 2 minutes left. We're gonna start it. I was late today. It wasn't. It was my fault today because I saw somebody I knew on my way here, and I had to talk to him. Anyway, but let's just say I start for every eigenvalue, I plug it in. I have 3 different values for lambda, 4, 2, and 1. I plug it in and I solve this equation. Okay, so now let's start with 4. 1 minus 3, sorry, 1 minus 4 minus 3. 3 minus 4 minus 1. What's the other? 3 minus 4 minus 1. Minus 1 and minus 1 stay the same. And now I have an equation that looks like minus 3 times VI equal to 0 because you do, oh yeah, I need to say how we do rows by columns, right?
Yes.
Yeah, so I take this, I multiply by this, and then I add this, multiply by this, and then I add this, multiply by this. But they are zeros, so they go away, sort of. Then let me get the red. I take this, multiply by this, I add this, multiply by this, I add this, multiply by this. And then that's how I get this. And it was like this, I got this, and then I will use green for the other one. I take this, I multiply by this, and then I add this, multiply by this, I add this, multiply by this, and I get this. Okay. What do you see here is with the 3 equations at the bottom is that, okay, VI is clearly 0, right? Okay. And then I have 2 equations that are the same.
Which would be any value in.
That gives me free choice. Yeah, free choice. I know that Vj is equal to minus Vk. That gives me free choice. I get an infinite amount of answers, of possible answers. And where is it infinite answers? Okay, let me finish it just to tell you. Free choice. Let's just say I set 1, and then I get the other one is minus 1. So my eigenvalue vector is, where is it? 0, I, 1k minus minus 1. No, 0, I, 1j minus k, right? It was my yeah, okay. But what do I mean by getting infinite number of solutions for that vector? Because it gave me a vector that is pointing in one direction. Say, what if I chose 2 for Vj, and then I got minus 2 for Vk? Wouldn't that work as well?
Yes.
It would have worked. Yeah, it would have worked, but the magnitude of the vector would be bigger.
Exactly.
So I'm getting a vector that is pointing in the right direction. Okay, this is a vector. But what if it's bigger? It's still pointing in the right direction, but it's bigger. And I know that if I take the vector's magnitude and I divide everything, I should get the same answer. So here, let's just say I use, let me write some stuff
I'm
down.
gonna use 2 minus 2, it's gonna be square root of 4. It should be 2.
It's gonna be.
Yeah. Is it the same answer?
It should be half j minus half k.
Yeah, so let's just say I chose this for my answer, 0, 1, minus 1. It's the same thing as saying Vi equals 0, Vj equals 1, Vk, excuse me, minus 1. Okay, what is the magnitude of this vector?
So for this example, we said we're gonna choose 2.
When did we say that?
2 and minus 2 is better.
No, no, I was gonna do that
okay.
later. I was gonna read with both to show.
Okay.
Yeah. Yeah, I'm doing that after. Yeah, so okay. 0 plus 1 square plus minus 1 square. Yeah. Square root of 2.
Yeah.
Very nice. Okay. Now I come here and I divide everything by square root of 2. I get this answer. Okay. Now, how about I do this? 2 minus 2. So VI, sorry. Anyway. Sorry. I hope there is nobody waiting outside. Well, anyway, I have this is 2. Oh, sorry, it's not 0. 0. Vj is 2. Vk is minus 2. Okay. Now, what is my magnitude? It's 0 plus 4 plus 4. Square root of 8. Square, square root of 8. Total?
Yeah.
Square root of 8 is
2 square 2.
Yeah.
2 square root of 2.
yeah, 2 square root of 2. Okay, very important. Okay, 2 square root of 2. So I come here and I divide by 2 square root of 2. The 2 cancel out. So I have the same unit vector of magnitude. It's the same always. It's gonna be 0 j minus k, right? So I'm giving you the right magnitude vector, but I'm giving you, you can give me longer. It's still pointing in the right direction. It's smart to give me the answer like this, like a unit vector in that magnitude. But I don't remember ever taking points from people giving me not the right answer. It's still the right answer, it's just a bigger vector, you know? Yeah. And there are 2 more eigenvalues that can be calculated using lambda equals 1 and lambda equals 2. And I think it's easier to do the other ones. I just, now that you know how to do it. Basically, yeah. Any questions before we?
And then when you have, you're gonna end up having 3 eigenvectors, okay?
Yes.
Which one you're gonna choose as your S1, S2, S3?
Well, it depends on the eigenvalues. The eigenvalue, I have 4, 2, and 1.
Yeah.
4 is the S1. 2 is the, but then every eigenvector is tied to the particular eigenvalue it came from, right? It's its direction. Yeah. And if I'm lucky, I will have a vector, eigenvector that is, say, 1i plus 0j plus 0k. It means that I align my vectors, my axes with one of them, right? And then that means I'm in a very lucky spot. But yeah, that's the whole idea for the eigenvectors. Yeah, people were getting confused last year when I was teaching the class. It was my first time, so it was much harder. I had a lot of mistakes going on, etc., etc. But they were like doing a homework or something, and they were finding different values for the eigenvector. But many times it was the right answer. It was just a longer vector. That's fine. It's pointing at the right direction. Because when you're asking for an eigenvector direction, it's a direction that you are pointing. Like it's not a, you can use this to show me the right direction, or you can use a long stick to show me the right. You are still showing me the same way, right? Anyway, thank you very much. If there are any questions? Okay, feel free to email me or message me, and yeah, we'll be back for more on Monday. Yeah. Yeah, today is Friday.
Because it will be my first one on Monday.
First?
Yeah, because the first one I wasn't here, the second one was a holiday.
Oh, yeah. Oh, your first Monday here. Yeah. Monday at 2:30. Yeah, we usually had a holiday every week.